This is going to be the lecture over chapter 7. Part of it, this will be the first part, and then we'll follow up with the second part. So, quality of X-ray beams. So, in looking for an ideal way to describe radiation quality, in other words, what type of electromagnetic radiation do we have? How do we do that? What's the method by which we do that? We're looking to specify the spectral distribution of X-ray beams. In other words, the energy fluence in each energy interval. How is the X-ray beam distributed among energies? And that's what it's attempting to describe. Now, that's going to be hard to measure. And in most clinical situations, seeing as how you're looking at things somewhat empirically, if you can take a look at the effect of what's going on, as long as you're ruling out being exposed to something that is so dangerous that you can't have any part of that in the beam, in most cases, you can just take a look at the effect and you're not really that concerned with the specific composition. In many ways, we go ahead and we give it a name, particularly for the linear accelerators that we do work with. But is it something that we need to know each and every part of the distribution? No, not really. And we'll get used to that as we go on through. The half value layer is one way, and it's fairly crude, but it does work. The more interest is in the penetration of the beam into the patient. Again, what happens when the beam interacts with the patient? What's going on there? And that's really more of what we're looking at. So how does the penetrating ability of the radiation, how is it described as or the penetrating ability of radiation is often described as the quality of the radiation. How deep can it go? When it comes to the half value layer, that's going to be used to describe the quality of the beam and the ability to penetrate materials of known composition. How does it behave? How do we know what it does? It's used for Bremsstrahlung photon beams, which has a spectrum of energies, but not for X-ray beams, whose energy is discrete and unique. In other words, if you were to take a look at cobalt-60, you have two specific energies. You don't really have a spread like you would in others. There you have two specific energies. So the half value layer is defined as the thickness of a particular type of absorber, however it's composed, that is required to attenuate the intensity of the beam to half of its original intensity. So for the low energy X-ray beams, the beam quality is described in terms of half value layer together with the kilovoltage peak. And this is because the beam is usually further filtered. So for megavoltage X-ray beams, the quality is specified by the peak energy alone. In other words, when you take a 6 MV beam, that's going to be the peak. That's going to be the maximum of what you see. And this is because the beam is already filtered through the target and the flattening filters so that no additional filtration is used. Now, we haven't really gotten into this yet, but the TMR, the tissue maximum ratio, is also used. We'll get to that next semester. It's not something we're going to focus on too heavily right now, but in later chapters, we will get to that. Now, the average energy is approximately 1/3 of the peak energy. So if we got a peak energy of 6 MV, 1/3 of that is going to be the average energy, or 2 MV. If you have a 10, then 3.33 is going to be your average energy. If you go to 18, then you're looking at the average energy being 6. So here you have a picture of a 200 kilovolt peak X-ray beam with various types of filters. You can see here that you've got the energy fluence per energy interval, and you can see the different photon energies as they go through. So you can see the K characteristic radiation of tungsten. You can see it here for tin. And unfortunately, I can't remember exactly what the C is, and I don't have it labeled here. The filters, the character of the energy spectrum of the X-ray beam, the effect of the X-ray beam filtered by 1 millimeter thick aluminum. The effect is so-called the inherent filtration. So the effects of attenuation, the glass envelope of the X-ray tube, the surrounding oil, the exit window of the tube housing, those can all be factored into this, and it's all equivalent to about 1 millimeter of aluminum. So the K characteristic X-rays produced in the tungsten target, you're looking at about 58 and 69, which I think we have already covered in a previous chapter. And then we have K characteristic X-rays produced in tin. Unfortunately, this is cut off and we can't see it. It should be available in the download here. Let's see if we can get to it. As a matter of fact, why don't we just go straight to that? Because usually the PowerPoint's a little more inclusive. It doesn't. There we go, 29.2 KeV. Combination filter, so you can contain plates of tin, copper, and aluminum, mix and match, accessorize, that kind of thing. You've got it designed to increase the resulting half value layer of orthovoltage beams without reducing the beam intensity to unacceptably low levels. You've got Thorius filters, you've got them arranged with the highest atomic number material nearest the X-ray target. So in orthovoltage range, these filters are often used to obtain half value layers in the range of about 1 to 4 millimeters of copper. So these combination filters, these Thorius filters are used. You've got Thorius 1, where you've got these combinations, you've got Thorius 2, and then you've got Thorius 3. And you can see here that you've got the order being important. You've got tungsten here, you've got tin here, you've got copper here, and then you've got aluminum. And you can notice the descending order of those materials. So with Thorius filters, you've got tin facing the X-ray tube and aluminum facing the patient, with copper sandwiched in between the tin and the aluminum plates. With aluminum filters, it's used in diagnostic and superficial X-ray energy range in order to harden the beam. And the HVL are expressed in terms of millimeters of aluminum, since that's what you're using. So for cesium and cobalt teletherapy, and I think I just realized something. Hang on just a second. Have this running in the background. That's not going to do us any favors. Let's see. Sorry about that. So for cesium and cobalt machines, gamma rays, filters are no longer needed because the beams are almost monoenergetic. There's no preferential attenuation by the filters. In other words, it's not knocking out specific energies, because you've only got, in the case of cobalt machines, you've got 2 different energies, and that's not, you don't really need the beam hardening. In megavoltage X-ray beams, the beam is hardened by the inherent filtration of the transmission target, as well as by the transmission through the flattening filter. And no additional filtration is required to improve the beam quality. So the half value layer is going to be 0.693, or the natural log of 2, divided by mu. And it increases with increasing filter thickness. Beyond a certain thickness, additional filtration may result in softening of the beam by Compton scattering. In other words, you're sort of defeating your purpose at that point. So here you have the measurement of beam quality parameters. You got your incident photon fluence, and it's going through a collimator and coming out here and striking through a particular material. You've got scattered photons going this way, and then you've got the transmitted photon fluence, which is being picked up by the detector. So you can see here the transmitted intensity graphed over here, and then you've got the millimeters of aluminum over here. And you can see for the first half value layer, obviously cuts it down to 50%, then the second cuts it down to 25, and then the third cuts it down to 12.5. So if you've got a narrow beam coming through here, that means you've got good geometry. Peak voltage, indirect methods are used to measure kVp without approach to the high tension circuits. The voltage divider, so you've got several high resistances are connected in series to form a resistance tower. And placed across the high tension leads, you can figure out what the voltage is, obviously by using Ohm's law, I times R. The sphere gap method, you've got high voltage lead of the X-ray tube is connected to a polished metallic sphere by a cable adapter. The distance between the two spheres is reduced until an electric spark passes between them. In the calculation of the peak voltage, you've got the critical distance and you've got the correction for air density and humidity, which can also factor into this. In that resistance tower, it's placed across the high tension leads. In the sphere gap method, you've got each high voltage lead is connected to a polished metallic sphere by a cable adapter. The distance between the two spheres is reduced until an electric spark passes between them. And by knowing the critical distance, the peak voltage can be calculated. Those are direct. This is more indirect. You've got fluorescence method, you've got the attenuation method, and you've got the penetrameter. So for the fluorescence method, you've got two different principles. You've got peak photon energy is given by peak potential. The K-edge absorption occurs when the photon energy is greater than or equal to the binding energy of the K-shell electron. Using materials of several different K-absorption edges can calibrate the kVp dial on the machine. All right, so you've got the measuring the radiation transmitted through the attenuator. So you've got your X-ray source, you got the diaphragm. You've got two different chambers here. This chamber, as I'd mentioned, measures the radiation transmitted through the attenuator, which is what you've got here. You've got a filter over here. You've got chamber 2, which measures the characteristics as well as the scattered X-rays, which the attenuator is trying to remove. And you've got the filter is trying to remove. It absorbs most of the scattered radiation from the attenuator. So using the K-edge threshold, you can see over here the ratio of transmitted to scattered radiation, and you've got the tube voltage. So you've got the kVp, which is the K-edge threshold of the attenuator. Attenuation method. The principle here is the observation of X-ray beam at high filtration. The slope of the transmission curve depends on the peak kilovoltage. The detector is going to be an ion chamber with 2 caps of copper, aluminum of different thicknesses. Calibration, determining the ratio of the detector response as a function of kVp of X-ray beams, accurately known peak potentials. Depends strongly on the waveform of the X-ray tube potential. So an unknown kVp of an X-ray beam can be estimated from the calibration curve. In other words, if you know how a certain thing behaves with something that you know the behavior of, then if you don't know this, you can match it up against a calibration curve that you know, and you can determine what your kVp is. The limitation is going to be your level of accuracy, and it depends strongly on the waveform of the X-ray tube potential. So for the penetrameter, you've got the principle here is comparing transmission through two materials with X-ray absorptions that change differently with photon energy. Structure is going to be polyethylene, rectangular central reference block. You're going to have identical metal strips, wedges, step wedges on both sides. You've got an aluminum wedge for the low kV range, and you got a brass wedge for the high kV range. So it's going to be radiographed in beam with heavy filtration and scattering shielding. You'll be obtaining the matching step position by using optical density ratios of adjacent wedge and reference areas and calibrate and measuring unknown kV. So comparing transmission through two materials with X-ray absorptions that change differently with photon energy. So using the Adron-Cook's cassette, a common version is going to be the Wisconsin test cassette, and it consists of film, which is partially covered with a slow intensifying screen and a fast intensifying screen. Matching step density with a reference depends on the kV and the calibration for measuring unknown peak voltage. Now, the effective energy, heterogeneous X-ray beams are consistent to express the quality in terms of the effective energy. The definition of effective energy of an X-ray beam is the energy of photons in a monoenergetic beam, which is attenuated at the same rate or having the same half-value layer as the radiation in question. So you can see some of the effective energies for the different half-value layers here of copper and for aluminum. Peak energies are half-value layers of lead or water. You can see the peak photon energy for those given half-value layers. So the mean energy, average energy, is the spectral distribution of a radiation field. Is going to be characterized with a distribution or fluence or energy fluence with respect to energy. In other words, it's going to be spread all over the place. So what's going to be the average? We're going to measure the complete spectrum of an MV X-ray beam. Calculation of thin target Bremsstrahlung spectra. We can also involve scintillation spectrometry and photoactivation. Practical method is done by using PDDs, percent depth dose, or TARs, tissue air ratios, all of which we have not gotten into yet, but we will. So this is just a very high level discussion of this. TMRs, or tissue maximum ratios. And we're going to compare the data with published data, like in the Hospital Physicists Association, or whatever your physicist is using now, in order to be able to determine that. Using the PAR method, or the photoactivation ratio method, you've got sensitive method of monitoring X-ray beam spectral quality. The process is irradiating a pair of foils, activated by the photodisintegration process. Use scintillation counter to measure the induced radioactivity in the foil. And the ratio of induced activities gives you PAR, which gives you peak photon energy. The ratio of induced activities gives you PAR, gives you the peak photon energy, and more sensitive method than the conventional method measuring HVL in water. So you've got the photon energy here, you've got the photon fluence or energy intervals, and the spectrum here, you've got the X-ray source going through a diagram, you've got the scintillation crystal, photomultiplier, lead shielding, the pulse height analyzer, and the scalar. So this basically gives you an idea as to what the fluence and the energy is for the given photon energies. So the measurement of energy spectrum, you've got electrons ejected from the crystal. That's what's going on in here. You've got the fact that they produce ionization and excitation of crystal atoms, which then produce light, which produce photons. I don't know why you'd say light photons. They strike the photosensitive surface of the photomultiplier tube, which is what we're talking about here. They eject low energy photoelectrons, which are collected and then multiplied by photomultiplier diodes, and then sort out electronically different size pulses by multi-channel pulse height analyzer, which again is not anything that I would ask you to do. The basics of this particular chapter is to realize we're trying to get at exactly what type of energy we have in our beams. You can do that through half value layers, but now, since we're talking about megavoltage beams primarily, we need to find or discuss the techniques that we're going to use in order to be able to do that. And most of the time, what you're going to be seeing is TAR, TMRs, PDDs, all of those kinds of charts. Those are the kinds of things that you would be seeing if you went and decided to make your physicist day and talk to them about, hey, how do you measure these particular beams when you're here alone on a Saturday night? Because that's what physicists do. And then if you really want it, and the physicist is eager, which most of them are, they're going to sit down and they're going to describe this process to you. So that's essentially what's going on here.